these sections we talk about how to determine the bending stress in a composite beam. Composite beam basically is a beam made of two different materials, and here for illustration, two different materials. Let's start from the beginning. Think about the principle where we obtained whatever we have done so far. So we consider from the bending strength. For example, for this demonstration, the upper portions about the neutral axis is under the compressions. So basically, this case is beam is curving up. Okay, it didn't show it here, but the beam is curving up, and this is a cross section, and so beam curving up basically like this. Okay, and the cross section basically is here. And assuming the two materials basically bonded so perfectly and no cracking, no fractures here. So here under this situation we can assume the distributions of the bending strength and it's continuous. Okay, continuous again 0 at the neutral axis, and then the linear distributions and the maximum at the top or at the bottom depends on the dimension here to here. Okay. On the other side, once we have the strain, then we apply Hooke's law and simply multiply the Young's modulus to the strain, we obtain the stress. And here come to the interesting part. The two materials and have the different material properties, which means the Young's modulus E1 should be in general shouldn't be equal to E2. So when we multiply the corresponding strain components, and we found the magnitude of the bending stress basically at the interface becomes discontinuous. And actually there's a jump in magnitude from material 1 to material 2 here, and it's basically showing in the graphing here. But for each material, that distribution of the stress is still linear, okay, and this basically the slope of this distribution is determined by E1. And again, this is in linear, and the slope is determined by E2. So that is the situation happens here for composite the beams, okay. And this kind of interesting phenomena, in essence, here we can conclude quickly, is basically here we for the things, because the different the slope in the distribution of the stress, and what we have learned haven't been able to deal with such a situation, which means the distributions, although it's linear, but the distribution is in different slope. We haven't dealt with this one before. And so that means what we have learned about, for example, determining the neutral axis, and that kind of formula basically finding the centroid of the cross-section, geometric shape, and as the location of the neutral axis, that is what we did before for homogeneous material, and then that doesn't apply here because the material is not homogeneous. Okay, so we need to come up with a new approach. Well, I would say we need to revise our method, our approach to deal with such a case, and that is the goal we're going to learn in this section here. So before we talk about how we're going to revise the strategy we learned before, and let us quickly review what we have done before. What is our strategy we learned for the homogeneous beam? Okay, homogeneous, that means a beam made of only single material. So if you recall the equilibrium equations, and that one is based upon which we come up with to derive and to determine the locations of the centroid, and through which the neutral axis is passing through. And so for this one, the equilibrium equation still applied to the composite beam, because for composite beam we only consider pure pure bending. So for pure bending, then this equilibrium equation should still apply. Okay, so we apply this equation to this case. So for this case, basically this the material basically divided into two domains in y direction. So from y1 to y2, that is for material 1, and from minus y0 to y1, that is for material 2. So basically this surface integral in terms of y, we can divide it into two domains. This is for material 1, this is for material 2. Okay, I simply divide carefully and to deal with the individual one. So the bending stress in material 1 is given by this number I plug in here. The bending stress in material 2 is governed by E2. Simply this one I copy here. Okay, so far so good. So this step is simply the direct implementations of these equilibrium equations. And since we kind of stuck here, so once we have this one, then we're asking ourselves, and how could we proceed and with a similar concept as we did before to determine the location of the neutral axis. Okay, so again, our first step, our first goal is to determine the location of the neutral axis. That is important. Okay, but we're kind of stuck here. And so we kind of thinking, then the people come up with the very smart strategy, and that is one here. If you look at this carefully, let me explain this one. So based upon this equation, I copy to here, okay? And then with this in mind, that we wish to, based upon what we have learned before, to revise the strategy for dealing with composite material. So we start from here and we play a little bit about mathematics. So you look at this carefully. And for example, we pick E2, we compare to E1, and that's an n-fold. So basically E2 equal to n times E1. Okay, so I will simply replace E2 as the m E1 here. Okay, and then I associate the n to b, so I simply move the n into this term here. Okay, everything moved from there, so the same thing here. And so this representing, you can see, is this one can be seen by this, and right now we simply place mathematics, and graphically it's basically showing it's like this. Right now I associate the n, which is the ratio between E2 to E1. I associate n to b. B is the dimension. This is the dimension in material 2. This is the dimension parallel to the neutral axis. So I associate the n, this scaling factor, to b. Graphically, basically is to say we scale this dimension and by n. So something like this. Okay. In this scaled dimension, basically material B2 in the cross section expanded like this. In this gray area, as different from the original blue one, okay, we call this called the transformed cross section as an entire one, and compared to this original. In this transformed cross section, you can see we look back at this mathematics. That one is just regarding the E1. So basically here we achieve what we try to say is we kind of homogenize using the transformed section, we homogenize the whole original problem into a single material per se in terms of the material property E1. So to this point, basically this integral representing is the integral of the gray area, which means the transformed cross section. So that means the integral we can combine together from minus y0 to y1, from here to here, and then from minus y0 to y1, from y1 to y2, basically it's across the entire cross section. So we combine together this one integrating is the area integral of this quantity over the transformed section here. Okay, so again, in this case, E1 rho is a constant. We can cancel from the both sides and leading to this quantity. So this quantity you can see get the formula with compared to the one we learned before. And so you can see that is the same concept, the same strategy. We simply is going to find this equation is representing is the location of the centroid. That centroid is pertaining to the transformed section. So for the composite material, and here let me make a quick conclusions, is this: we get the transformed cross section. On that cross section, we proceed and the steps, the procedures of finding the centroid of the transformed cross section. That centroid locate the neutral axis. Okay. So basically, they dealing with the composite sections, and then basically is our strategy is to get it transformed. Okay, and to get the transformed section, basically the things is this: I homogenize the whole material in mathematics to this kind of transformed section using the material one as my reference. Okay. So you can also pick the material 2 as your reference in the way to homogenize material 1. So kind of the either way would be good. Okay. So here I summarize the steps and for determining the bending stress for composite beam. And the first portion is, again, we need to determine the where locations where the neutral axis is. And that one basically again is depends on implementing this equation. This equation again saying the centroid of the transformed cross section, and we need to determine the centroid of the transformed cross section and through which the neutral axis is. Okay, so that step is this: you pick a reference material. For example, I pick material 1 as my reference. And then for homogenization, to homogenize, that means I try to transform the whole thing in terms of grade, in terms of the reference material. Then once you pick, for example, this as reference material, you simply calculate n equal to ratio of the E2 over E1. Okay, so E1 divided by your reference material, E2 is the other one. Okay, divide by Young's modulus of the picked material of the reference material, you get n. Then you scale the dimensions of material 2, and that dimension you need to pick is to parallel to the cross sections, or to the neutral axis. Okay, look at here. For this material 2, they have 2 dimensions. One is this dimension, one is this dimension. And for this province, because this is the beam is curved up, okay, again, this is a beam, something like this. Okay, and then here we pick up the cross section is from this view. Okay, we pick up this view. So this is a cross section here. So here, this is a neutral surface here. So that means accordingly, this is the direction of the neutral axis, and neutral axis should be in that direction. So you need to scale the dimension that parallel to the neutral axis. This is a key point. Okay, this is a key point. Let me emphasize one more time. This is the key. You need to scale the dimension that is parallel to the neutral axis. Okay, so once you scale the B to say NB, then you obtain your transformed cross section here. Then the remaining simply is to repeat what we have learned before to determine the centroid, and then the neutral axis passing through the centroid here. Okay. Once you determine these the neutral axis, then simply you calculate the moment of the inertia respect to the moment of inertia of the transformed sections, okay, you determine the moment of inertia of the transformed sections, okay, and I using this notation T as transformed section, okay, and then on these transformed sections you simply proceed. For example, you want to determine the maximum stress, that will be on the top or at the bottom here. So you determine those one using whatever the formulas we learned before, okay, and then you obtain the stress over the transformed sections. Then in the final step, you need to get that stress being converted into the real stress that is happening on the original section. So that can be done by this. And over the reference material here, we pick from the beginning as material 1. The stress being calculated from the transformed section is equal to the stress here. However, for this transformed material 2, the stress calculated here, you need to multiply by n and to convert it into the real stress happening in the original here. Multiply by n, multiply by n. The reason here, I give you the formula, you need to multiply by n, and for whatever the stress you calculated from material 2 to material to the original here, okay, multiply by n. Again, let me repeat it again, multiply by n. And the question, why? Here I can leave you this question for you to find the answer from the textbook, okay, and that is very easy. You think about it a little bit and before you reach the textbook for reason why, and otherwise drop me an email, I can try to answer to you, okay. Here we can take a look at one example here. So here for this example, assuming we want to have the bending applied, and this is the case here. So this is the original beam, okay, and then here, for example, we apply the bending in these directions here. So for this case, this is the orientations of the neutral surface. I would say orientation. I don't know exactly the location yet, but here I know the orientations, okay. And then let me put the cross section. So from the side view here, if you're looking from here, that's the side view, okay, and from the side view, this is the orientations of the neutral axis, okay. So right now the neutral axis, in looking in this view, so this is, let me say this is the y direction and this is the z direction, okay. So that's the y direction, z direction here. So this is our neutral axis orientation, like this one. So for this case, we want to determine, here we given this is a bending, we want to determine the maximum stress here, okay. So for this case, again, we can proceed our calculation. So here is a strategy provided by textbook, you can take a look at, and then here we can see in details and how to proceed here. So for this case, the step 1, we need to determine the location of the neutral axis, and for this simple shape, and it is very uniform, we can see here I pick brass as my reference material, okay. Then in this way, the steel is the one I need to homogenize. So in this way, I need to first determine the n equal to the Young's modulus divided by the reference material, and that is the other one, okay. So that reason we kind of write it up here. Here we determine n equal to this number. So once the n number is determined, then we're going to homogenize the steel, and so that means we pick the dimensions. Earlier we have determined this is the orientation of the neutral axis, so that reason why we pick this dimension to scale up. So scale this dimension 0.75 by 1.933. So basically this is 0.75 multiplied by n equal to 0.75 and then 1.933. Okay, then we have this number. So this is our transformed section. Okay, and then we calculate the moment of inertia on this transformed section here. Okay, So that is this one here. Okay, so this is, let me emphasize, this is the I moment of inertia on the transform section here. Okay, so then we calculate the maximum stress, and you should know maximum stress for this can happen at the top and the bottom, and because of the dimension the same, the distance here the same as the distance, so in terms of the magnitude they should be the same. So we using this magnitude calculation, m equal to what we are given here from the previous page, and this dimension is 1.5 y, okay, and I is this one we calculated over the transform section, so that's the magnitude. And now we convert it back to the original shape. For brass, that is our material, so for brass, that is our material, and based upon which we reference on. And so that means the stress is the same from transform to original, that is the same. And for steel, that is the material we have been homogenized. Okay, so that means if we multiply n with the stress calculated on the transform, and we obtain the stress here. Again, here I want to multiply with n, so that is the part I emphasize here. In this page, again, I emphasize a couple times, and you calculate the stress over the transformed section. And for material 2, once you convert it back, you need to multiply by n. So that is a 1 here, and that is important. And again, why? Look at our textbook. That reason is very simple. So this is a simple demonstrations of these transform sections. And here I have 2 more, I would say a little bit more rigorous example here. And here you can refer to the solution process that demonstrated in the YouTube in this channel. And this basically here, let me explain a little bit. It's going to, this is a section, this is a beam, okay? And let me put into 3-dimensional case, okay, put into like this, and then here is hollow, something like this one here. This thing is going to bend about the horizontal axis, and let me explain this one to you what that means. And that means, let me, before doing that one, I need to place my axis, the coordinate system x, y, z, okay? This one is bent over horizontal axis, and here the horizontal, that means here let me take xz as our plane, and that means our horizon. Okay, so for this case we want to bend around the horizontal axis, so that means we're going to bend about the z-axis. So this is basically is bent about the z-axis. Okay, so bending about the z-axis, and let me put the bending moment here, and so bending about z-axis, and that means here the bending should be in this way. Okay, basically they're going to curve up or curve down, either way. Okay, and why this bending is in bending about the z-axis? Again, if you apply your right hand rule and your thumb aligned to this direction, so let me put into the double arrow notation here. So you can see this double arrow basically is in parallel to the z direction. So that is the reason why we said this bending is about the horizontal axis, about the z-axis, about the horizontal axis. So this bending is bent over horizontally. Okay, so that is a case we identify the bending horizontally is in this case. So here is a solution for you to for your reference, and again refer to the YouTube channel, and that's a detailed illustrations of the steps there. The same problems, and we're going to bend about the vertical axis, and again let me explain that one here. So here is our original undeformed beam, and let me put into 3-dimensional drawing here. Okay, there's a hollow here. So again, let me defined my coordinate system x, y, z. And now it's a bending about the vertical axis. So here y is our vertical axis. Okay, so that means it's about y axis. So again, you can see apply the bending, apply the about the y-axis. So can you imagine? So basically at the two ends here, let me plot it. So about the y-axis, about the vertical axis, and right now that is a double arrow. For example, either up or down. Here I pick up for illustration. So again, apply your right hand rule. Align your thumb to the double arrow, then the other four fingers basically is to tell you the orientations of the moment. So that moment should be in this way. Okay, so the moment should be vertically, this is the vertical axis in that way. On the other side, this is the vertical axis, the moment should be in this way. So that is a moment. Okay, so under that situations, let me try to plot the transformed, the how the beam will be bent. So let me plot this plane here. So the deformed beam will be something like this. So that's going to curve into, let me pick this line for my reference. I don't want to mess up. So that curve will be basically curved in the XZ plane. Okay, this curve, this line will be curved in the XZ plane, in this case, under this kind of the loading. So hopefully you can see the kind of the give you a good feeling. Okay, so with those things in mind, then again you go to this YouTube channel to go over with you and with the solutions here and for the details how this thing is being explored here. And I found the two questions are pretty interesting, and then that can verify totally whether you understood the topics we talk about here. Okay, great. So here is the second question, and this is the first questions. Okay, so good.